So first we're going to discuss a little bit about the physical properties of alcohols and alkyl halides, and I'm going to go really quickly with it, just because it should be a review, just based off of its chemical structure. You should be able to figure a lot of this already out, and then I hope to spend more time on on the chemical preparation of them. Okay. Obviously, alcohols and alkyl halides are polar. Okay. Now, once again, we've already talked about, is there a polar moment versus just being a polar molecule? And for example, CF4, which is tetrafluoromethane, you should already know how to do that. It's overall, even though they're individual dipole moments, overall they cancel out, so it'd be nonpolar. Alcohols they can do hydrogen bonding, which we're going to get to in just a moment. Okay. Which make it even stronger types of bonding than you would find within the alkyl halide. Okay, and so this just shows you, once again, gives you an idea here about the boiling point. You're going to see a similar trend if you looked at melting point. But if we had propane versus fluoroethane and ethanol, size-wise, they're all very similar. However, you can see the changes. Propane is a gas at room temperature. Fluoroethane increases. It too is a gas, but it's increased by 10 degrees. And then we have ethanol, which is a liquid at room temperature. In fact, it boils at 78 degrees. And so why would that boiling point of ethanol be so much higher than even the fluoroethane? What can ethanol do that fluoroethane cannot do? Hydrogen bonding. Okay. Since it's so highly polarized, and remember, they can reciprocate with each other. So that's why you can have two alcohols, as they're showing here in this picture. You can have two alcohols performing a hydrogen bond between each other, and that just makes it much more difficult, or it requires more energy in order to break that apart, in order for the molecules to escape from one phase to the other. Remember, when we're going from a boiling point, or we're using something at the melting point, this is not a chemical reaction, it's a physical reaction. You are not, because I've seen people pop this off, and no, that doesn't happen. All it means is that this ethanol and that ethanol are being separated from each other. They're no longer interacting, or they're having less of an interaction with each other, depending upon what state of matter it is. Remember, hydrogen bonding only occurs between oxygens, hydrogens, nitrogens, and to a lesser extent with fluorine, but only for hydrofluoric acid is considered a type of hydrogen bonding. So that's why even biochemistry, organic chemistry, we don't ever talk about it. Gen Chem books would slip that in there, considering the fact, but once again, it's only hydrofluoric acid. So that's why fluoroethane cannot hydrogen bond, because there is no reciprocal hydrogen on the fluorine. Okay. Hydrogen bonds are directional, and so that means that they do have some sharing of the electrons between them. Okay, and so it's not really covalent, but there is some sharing of the electrons. This next table just comes from your book, and since it just kind of gives you an idea of how the boiling points increase, it should make sense. We've already talked about this earlier. The boiling points is going to increase, or melting points, as you go with molecular weight. Boiling points of alcohols are higher than what you'd expect due to hydrogen bonding. And once again, as the polarizability increases, the boiling point increases. So, what does that mean about polarizability? So we know what that means. I like to use a very non-scientific term for polarizability. That's jiggle factor. So the larger the electron cloud, the more easily it is to polarize. That's why iodine, because remember the nucleus itself is still so ridiculously tiny compared to the electron cloud. That's true for hydrogen, which is the most simple, to big old iodine, which is a big old fat thing. So it's more easy to polarize that iodine, because you can figure that it's easier to get more of the electron density at a split second in time, probably more like a femtosecond time, to have more of it electron density on one side versus the other. And so this just shows you, especially this is true here, the larger the halogen, the greater the polarizability. So the more easier it is to perturb the electron cloud. They don't really show you a picture of it. And so we can imagine by adding more and more chlorines here, it becomes a larger and larger electron cloud. So that means it's going to be more easy to distort the electron density, and because of that, it's easier to have split moments whenever there's more electron density on one side of the molecule versus the other side of the molecule. Okay. Oh, please note that the fluorides is different, and it doesn't follow, it bucks that trend. It's just like a little asterisk. And some say it's because of the fact that fluorine is so electronegative, it's just not polarizable at all. Okay, and so, but all the others, chlorine, bromine, iodine, that's true with all of the others, but fluorine is an exception. This should make sense. As I mentioned, we're going quickly on this part. Solubility. Alcohols can hydrogen bond with water, so therefore they typically are water soluble. However, that being said, if it's something that's really, really, really long, whoops, that's supposed to just be a regular carbon, and you just have that tiny alcohol on the end, it's not going to be water soluble because the hydrophobic portion of this molecule here is so much larger than anything else that it overwhelms the hydrogen bonding capability for the alcohol. It's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So that's one decanol. And so its solubility will be essentially zilch in water. Okay. However, methanol it's highly soluble in water. Methanol, ethanol, a lot of those, because they're small. Alkyl halides typically are usually insoluble in water. Okay. Another example of an alcohol that's not soluble in water is cholesterol, which we hear about cholesterol, biologically. It does have an alcohol on it. It's this huge, multi-cyclical, organic compound. It's got 1, 2, 3, 4 rings. Yeah, 4 rings, and then there's one little tiny alcohol that hangs off. And also off the very far ring, there's this really long alkyl chain and everything. So it's highly hydrophobic, even though it has that one little alcohol hanging off at the end. Okay. So now we're going to get to new stuff. So how can we make an alkyl halide from alcohols? And this just shows you, this is not a reaction mechanism or even a reaction scheme. This is just a chemical equation. And so what it requires is we have an alcohol, a hydrogen halide, so like hydrochloric acid, will make the alkyl halide, and then water. Okay, so we saw this kind of stuff in Gen Chem. You probably used these kinds of reactions in learning how to go from moles to grams and figuring out percent yields and all that kind of stuff. But now we're going to actually start talking about the mechanisms that are involved. Okay. So this switcheroo kind of reaction, where we literally are taking one functional group and swapping places with another functional group, is called the substitution reaction. They probably use terms like metathesis in Gen Chem, but this is a substitution reaction. Okay, now we're going to start talking about reaction mechanisms. Those are your electron pushing mechanisms. Electron pushing mechanisms. Some books also like to call it curved arrow notation. It's the same thing. We've already discussed it when we were talking a little bit about resonance structures, and also gave some really generic examples like in chapter 1 or 2. But curved arrow notation. I probably will never ever call it curved arrow notation again, because we just always learned it as electron mechanisms or electron pushing mechanisms or reaction mechanisms. Okay, so we have a rule of thumb. We actually have multiple rules of thumb. Follow and if this was like the old match game, blank. Well, in organic chemistry, it would be follow the money. It's follow the electrons. The electrons do all the work. Whoops, it's supposed to be electrons. The electrons do all of the work here. Even when we talk about a protonation reaction, where we're talking about a proton being added to something, it was because electrons came and smacked that hydrogen to take it away. All right, so never, ever, ever show the arrow going from something more positive and attacking something negative. It's always the electrons doing. And so that's why I think we already talked about it. Normally we're talking about the electrons going from something that's negatively charged and attacking something positively charged. Or it could be electrons going something negative to something that was delta plus. Whoops. My delta didn't come out well. Delta plus. You can also have delta minus going to attack positive. Does anyone want to venture what the last one is? Delta minus attacking. Not necessarily neutral, but delta plus. Because we're always talking about positively charged, or things that are electron deficient. Just think of it that way. Things that are electron rich has to attack things that are electron deficient. Okay, another rule of thumb. That one's a really big toe. We're going to use a term called nucleophile. Which, what do you suppose that means if you think back to etymology? Not etymology, was it etiology? Whatever, the origins of words. Phile means attracted or loves, and then nucleo would be the nucleus. Okay, so nucleophiles are what nucleophiles do the attacking. Typically, there are different kinds of reaction mechanisms that don't have a nucleophile per se, but nucleophiles do the attacking, and nucleophiles must have lone pair electrons. They don't have to be negatively charged, but they have to have lone pair electrons, or otherwise they can't go out and do the attacking. Now, if you have a single electron that goes and does the attacking, it's called free radical. Okay, just a little bit, and I'm going to abbreviate electrons that way. Let's see. So I had a third rule of thumb that I was going to do. Follow electrons. Nucleophiles must have lone pair electrons. Oh, the next one actually would make more sense after we do an example or two. Okay, so I'm going to go on from there. So the easiest way, I know if you follow the PowerPoint goes over reactivity trends and things like that, but to me, it makes more sense to work through some of these before you go over trends, because otherwise you just have to take my word for it and it wouldn't necessarily make sense. All right. One other thing I wanted to bring up is the fact the nomenclature, like they like to use abbreviations. So when we're talking about reaction mechanisms, many times what you'd see is something like this. Okay, that's a big capital S, subscript capital N, and a regular number 1. Or you can have a regular number 2 there, but I'm just going to let you know what each of these mean or indicate. So, that means it's a substitution reaction. Using a nucleophile, which a lot of times we abbreviate nucleophiles as just Nu with lone pair electrons, which after learning the rule of thumb, that should make sense. So they even call this nucleophilic substitution. The hardest part is this last one here, that 1. That is the one that people struggle with. And what that is this tells you, it technically gives you the idea of the rate law, like it's called if you think way back to Gen Chem, it's called molecularity of the rate law, but that's just a really difficult, like why you learn that vocabulary, unless you're going on Jeopardy or something. But what it does is it tells you, here, let me do a better job. I like it. In rate limiting step, the number of molecules the rate, that's supposed to be rate, depends on. So if you remember back to Gen Chem, I think we covered a little bit in Gen Chem 1 and more in Gen Chem 2. There's like zero order and first order and second order and all that kind of stuff. This literally tells you that in the rate limiting step of the entire mechanism, these mechanisms have more than one step to them. Whichever one's the rate limiting step, it only depends upon the concentration of one thing. Even though there may be multiple things around, only one of them affects the rate. Sn2, it'd be the concentration of two different things would affect the rate. So for example, in Sn1, if you double the concentration of whatever that is, you're going to double the rate. And in Sn2, if you double it, it's going to quadruple it because it's 2 squared. Okay, if you double both things, I should say. If you double only one, then it's going to have different differential effects. So that's why the first one's called an Sn1 reaction that we're going to go over. Let's see. Well, let's get rid of that one. So an Sn1 reaction. I'm going to do a very specific example here, rather than using a generic R. Okay, and so at this point in time, I would expect you to know how to name this. This is the overall reaction. This is not the mechanism. Please note, almost always when we talk about like hydrochloric acid or any of these acids, with the exception of like acetic acid or something like that, they're strong acids. So if you think back to Gen Chem, they don't really exist as HCl. They exist as H3O plus and Cl minus. So get used to seeing it written this way, where they just ignore the chlorine for the time being because it's HCl plus and a Cl. I mean H3O plus and a Cl minus. And that's important because whenever I do the mechanism, it's going to look like this in the first step. Okay. So I'm writing it this way. The book, sometimes will write it as HCl. Come next semester in particular, you'll never see it written HCl. You'll only see it like H3O plus, Cl minus, or even just H3O plus. So that's why I want you to get used to seeing that. Okay. We have another rule of thumb before we get started. When you see an acid protonate, because that's what acids do. Anytime you see an acid around, it's there for a reason, and that's because it's going to give up its proton, which overall is what happens here. If you leave it as HCl, the H is going to go away. We'll find out in a moment. The H is going to go away because it's going to be protonated. If you leave it as H3O plus, it's going to go away to make a water. Once again, I'm leaving it as H3O plus, so that way you can get used to seeing it later on, looking that way. Okay. So we have a proton. We have an acid right here. So that means we will be protonating something. So now I'm just going to redraw this and move all this out of the way. Because I don't have as much room as you do to work with. Once again, the Cl minus is around. And technically, I'll leave it here, but if you think that's supposed to be Cl. But if you think back to Gen Chem, at this first point, it's the spectator ion. It's not doing anything right now, this first step. So, let's just work our logic through this. What do we have here that's electron rich? We have a couple of things here that are electron rich. What's one thing that we have that's electron rich? I'd say there are no wrong answers, but there are. But just don't be ashamed if you say wrong answer. But what's one thing that's electron rich? The chlorine. What's another thing? And that's true. It's going to come and play later on. What's another thing that's electron rich? Oxygen. It has. Remember, what's the lone? Kind of gave it away. What's the rule of thumb with respect to nucleophiles? Lone pairs. Okay, so we have a couple of things. We've got three things there that lone pairs. We've got the chlorine, which I just didn't draw them in yet, and we have two oxygens. Of the two oxygens, which one do you suppose is going to be more likely to do the attacking right now? Because it's more electron rich than the other. The one in the alcohol. Okay? So remember, there's another rule of thumb. When you see an acid, you protonate. Okay, so I'm going to use a different color. Whoops. What that means is we have some electrons. They're going to go and they're going to do the attacking. So remember, the rules of thumbs are things that are electron rich always attack things that are electron deficient. And another rule of thumb was when you see an acid, you protonate. So what do you suppose this oxygen here on the alcohol is going to go out and smack? It's going to be H3O+, but what part of the H3O+ in particular? So your gut feeling is to say, oh, the oxygen, because the oxygen's got the positive on it. However, it's not this time. And I'll draw the reason why. I didn't want to just draw that out. Is because if it goes and it attacks it, boom. This is going to be what the product is going to look like. You always draw, and like I said, don't draw this because it's wrong. Sorry, I spit all over this. This is the oxygen that did the attacking. It has its hydrogen. It now has a new bond to the oxygen that was attacked. That oxygen still has 3 hydrogens on it. And lone pair electrons. So there are lots of things wrong with this compound. All right, I mean, what's one thing that you can just pick out and say, that's wrong? It's violating the octet rule. Okay, so we have this right here. This oxygen here's got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Okay, another thing that's not very good is if we look at the formal charges on it, they're going to have incorrect formal charges. I mean, they're just bad things that are happening. 1, 2, 3, 4, 5, 6. Because this right here is going to have 1, 2, 3, 4, 5. So it's going to be positively charged, and you have one violating the octet rule, you got another one that's positively charged, and you have Cl minus around there. And so that, like I said, is not correct. Oh, I did the wrong one. Oh, see, now it won't even let me. So, here, I don't like that. So I'm just going to redraw it. So we already know what one did the attacking, because that was correct. But what else do we have? And I'm going to draw the chlorine in just for clarity's sake right now. What else do we have around here that's electron deficient? And remember, what's the one rule? When you see an acid, you protonate. So what do we have in H3O+ that's electron deficient? The hydrogen. It doesn't matter which one. And because even though the oxygen is positively charged, it's still more electronegative than the hydrogen. And so that's what acids do, is they protonate. So what we have here is this goes out, reach out, smacks, boom. Sound effects optional. Something has to break or give, because otherwise we'd have a hydrogen that has too many bonds around it. So what can break or leave or give right here? It comes, and it's literally coming, this oxygen here with its 2 electrons is coming and it's taking that hydrogen. So what has to break or leave or give up? The bond between the oxygen and that hydrogen. That's called a leaving group because it leaves. So these two electrons right here stay with that oxygen. That's why it's called a protonation step. And also another rule of thumb is many times this is reversible and fast. So now you draw what we have. Draw everything that didn't change. And the technical term for this first step is called protonation of alcohol. The original alcohol only has one lone pair electron now. And it has the hydrogen that it took. And what had been H3O plus is now what instead? It's just water, yeah, H2O. It's perfectly fine and dandy. Now you, at the very end, whenever you write this all, you always want to check and do all the formal charges. Is anything going to be charged here? Yes, this oxygen, this new one is, oops, wrong color, is positively charged. But you always have to have conservation charge. Remember, I didn't draw it in. The chlorine anion is still around. This was the protonation step. Okay. It's usually fast. It's usually reversible. That means it's not the rate limiting step, because a rate limiting step by definition has to be not fast, but slow. So in the entire mechanism, it's the slow one. So the next step is the rate limiting step. So what happens here, it's called the dissociation of water to form the carbocation. So at this point in time, these two electrons here that's between the carbon and the oxygen leave to go with the oxygen. Usually, it actually favors the alcohol formation. I wouldn't be a big particular on you knowing that. I can't say that the online quiz that it does, it may ask you one way or the other. And so one of the reasons, or one way that you try to get around that, is you use as concentrated acid as you possibly can to have it favor going in the forward direction. So all of this stuff stays the same. The chloride is still there, the water is still there, none of that has changed. Okay, so now we just draw everything that stayed the same. We still have this. We have, I'm going to try to keep it color coordinated. That water. And technically we have chloride, and we have the original water as well. Okay, what is missing right here? The positive charge on the carbon. Because it does not have a hydrogen there. Because that carbon didn't start off with a hydrogen on it. What kind of carbon is that? Remember, primary, secondary, tertiary, quaternary? What kind of carbon is that? Tertiary. By the way, this is called a tertiary alcohol. An alcohol that's attached to a tertiary carbon is called a tertiary. Just like a primary would be attached to a primary carbon. Secondary alkyl halide means it's attached to a secondary carbon. All right. So this is the rate limiting step. And so it's fine with me. You can either write RLS for rate limiting step. You can write slow. It's the rate limiting step. Either way is fine. Okay. And technically it was called, once again, it was the dissociation of water to form a carbocation, because that's what we formed. So then we have our last step. It's fast as compared to the middle step. That's why it's not the rate limiting step. What do we have here that's electron rich? That can be a nucleophile that can do the attacking. There are a couple of possible answers, but what's one of them? The chloride, and that's the correct answer. You could have said, oh, well, the water could, and that's one of the reasons why we say it could go backwards. Because if it does, it's just going to form the same thing. But that's the chloride, and so what will it attack? What is electron deficient that is easy to attack? That carbocation. Boom. Sound effects optional. Please note, once again, it's a double-sided, double-pronged arrow, or double-barbed, I should say, double-barbed arrow. So now we just draw, and I would expect you to know how to name this at this point in time, because you already know how to name alkyl halides. And technically, we already have water. Water is another product. In organic chemistry, we're usually only worried about the organic products, unless you're told otherwise. And at least on my exams and quizzes that I give in class, anything like that, usually we aren't too worried about the inorganic, like water. You can still feel free to always get in the habit of writing it out, and I would hope you know how to name water as water. But what's the name of this compound going to be? What's the longest carbon-containing chain for the alkyl halide part? 3, and so its root word would be prop. What's the ending going to be? Someone say it, but say it with conviction. Ane, because they're all single bonds. Now we have locants. We've got that locant, and we've got this locant. Which one's going to come, not locant, substituent. Which one's going to come last in alphabetical order? Methyl. We have to give its locant, we have to give its number. What number is it? 2. And then the Cl would be called chloro, and its number would be 2. So this is 2-chloro-2-methylpropane. The rate law, which is that, remember, this is called an Sn1 reaction. So if you think back to Gen Chem, every rate law begins rate, or sometimes they would use V for velocity, reaction velocity. What does every single rate law, regardless of the order it is, every single rate law has what letter in it? There's always something right here. This is something you should know. What letter of the alphabet is there? Nope. It's for kinetic rate constant. What is the kinetic rate constant? Someone said it, I think. K, and it's always, and this is important, it always must be a lowercase k. If it's a capital K, it means it's a thermodynamic constant. Lowercase k means it's a kinetic rate constant. Then, this is where we have to look at the rate limiting step. This was the rate limiting step, and please note, there is only one species here that's involved, and that's the dissociation of water from the original compound. Though this water and the chloride had absolutely nothing to do with the reaction. So that's why this would be, its rate is equal to the concentration of, that compound right there is called an alkyl oxonium ion. And so some people like to call it the ROH2+, because that's what it looks like. But knowing the parts of words, it should make sense why that's called, because it has an alkyl group. Oxonium just means it's a positively charged, oxygen there. Because remember, IUM means it's a cation. Okay, so that's why it's a rate. That's why it's called as Sn1 reaction instead of Sn2. Okay, so that's why this reaction, it doesn't matter how much of the HCl that you have around to begin with, because the rate, the overall rate for it, only depends upon this step, which that's not involved in that step at all. Okay, it only depends upon the amount of alcohol you originally started off with. Okay, all right, so let's start talking about trends. That's why I didn't want to give you the trends first and say you memorize this real quick before we work through the mechanism. The reactivity of the hydrogen halides parallels their acidity. So HI, hydroiodic acid, would be the fastest, but it's so reactive that bad things can happen. HF is too slow. So what you will see over and over and over again, HCl and HBr are the two that are used typically in protonation reactions. So those are like the Goldilocks. In fact, next, I can't remember if it's later this semester or the beginning next semester, we'll talk about that in greater detail. Sometimes you want to use the chlorine, sometimes you want to use bromine and things like that. But you could use at this point in time, either one is fine, HCl or HBr. The alcohol depends upon, they like to use that term, substitution pattern, blah, 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 blah. So this is where it's just easier to say the tertiary alcohol is the fastest, secondary alcohols are intermediate, and the primary alcohols do not go through Sn1 reactions. They're too unreactive. Does anyone want to venture a guess why? Or actually, perhaps I should tell you, well, I shouldn't. I want you to learn the logic. Don't just sit here. You will not be able to memorize every single mechanism throughout Organic Chemistry 1 and 2. You need to learn the logic. Learn some basic rules. When you see an acid U, say it with some more. Come on, U. Let's freak the math people out. Every time you see an acid U, protein. Thank you. Okay, so that's one rule that you need to know. You always follow nucleophilic attack. You always follow the electrons. The lone pair electrons will go out. One of the collaborators that we used to have, I was already at medical school, and so I didn't ever have a class with them. Technically, he was at the University of Maryland, and we were at University of Michigan, but we collaborated with him. But every time I heard him give a talk, I really wondered, I thought, people who were in his class, they had to think he was really weird. But you know, it helps people remember. He'd always say, you go after and you attack the lowest hanging fruit or the child in the street. He said, because they're the easiest one to pick up. I was always kind of troubled by the fact that he's trying to pick up children in the street. But that's why you go out and you take that hydrogen. It's the lowest hanging fruit. It's easier to pluck off that and attack that hydrogen to the protonation and give off water than it would be to try to attack that oxygen and have that really weird mess. Okay, so you always go after whatever is easiest. So I said that this trend should make sense in this. Let me go. That's kind of hard to say. Because if we look at, I'm just going to show you the rate, because I don't want to draw it all again, the rate limiting step. The rate limiting step in the one that I just showed you, that specific one, using 2-propanol. Remember, this is what it looked like. Okay, and the water was leaving. It was taking its electrons and leaving. And it was going to form this compound right here. A carbocation in water. Of course, water is perfectly happy. This carbocation is not happy. Okay? It is not happy. It is not going to remain a carbocation. That's another rule of thumb if you want to write it down. I don't have that much room. Your final product will never have a carbocation in it. Or a carbanion. Carbons want to be neutral. So their formal charges will never be, I can't, there may be exceptions. I cannot think of one, but it will not be a plus or a minus. Okay, you want them to be neutral. So why does it make sense that if we look at the trend, the tertiary carbocation is the best, followed by the secondary carbocation. And then these carbocations are the absolute worst. In fact, they're methanol, so CH3 plus, does not ever form. Like it does not work, okay? That's a big no-no if you ever show that. And even the primary carbocations are not happy. So that's why I put the 2 greater than signs there. What does the tertiary and the secondary have that the primary and the methyl doesn't have? Maybe just state the obvious. More carbons. So the way I'd like to think of it is this is electron deficient, right? You can almost think of electrons and electron density as currency, if you want to think of it as money. This one, it's not happy, but it's more happy than these down here. And the reason why, there are technically two scientific terms for it. One's called induction. The other one's called hyperconjugation. But I can give a real-world example in a way. Whoops, sorry, I used my right hand, so it's kind of sloppier than normal. So it's got more friends to help it out. So what induction means is that the neighboring carbons can lend some of their electron density. No, not that one, but these three, they can actually lend a little bit of electron density to help out their friend, help out their buddy who has a positive charge. It's not, you don't want to do that forever, but you can in the short term to make the reaction go. Hyperconjugation is a little trickier, but what it means is each of these, well, that's supposed to be an H, each of these have a hydrogen. And remember, they are all equidistant. Even though it may look from the way I've drawn it that 3 of them or 6 of them are closer than the others, they are in 3 dimensions. They are all equidistant. In fact, this compound here goes from sp3 to an sp2 intermediate. Okay, so that means they literally are 120 degrees from each other. So these 9 hydrogens here in hyperconjugation, what that means is they can almost form, it's similar to a pi bond. Remember how there's that overlap from the electron orbitals, the side-to-side overlap? These 9 hydrogens that are all the same distance from that carbocation can also come in and help out some by lending electron density. They kind of protect that sensitive spot right there. And so that's why a tertiary carbocation is much more stable than a secondary. A secondary is much, much, much more stable than a primary because it would only have 1 carbon to help it out. And methanol, what would be methanol? So the methyl carbocation has no friends. And so it does not form carbocations at all. So that's why when we talk about the next class, well, technically I'll just show you more about this. So this is what this is all trying to say. And it gives examples here about how the tertiary can react in minutes. Secondary requires HBr. HBr is a stronger acid than HCl. And it requires you to go to higher temperatures because it's not very happy, especially if you want to do a primary. So that's why it's just unrealistic for a primary alcohol. Okay. So here, like you can see that, this is ridiculous. So the temperature or pressure, sometimes you can do it with pressure. So what are we doing here? This is the reaction scheme for it. Let's see if go back. Every one of these has a transition state. You didn't have to memorize all that. That's the electron pushing that I just did. Except once again, they show HCl instead of H3O+, but I want you to get used to seeing H3O+. But I wanted to show you this part. They break it down. I'm not going to go through all of them right now on your own because it's already available. It breaks it down like step by step. So we can see here, we started with this. You get the protonation step, which it takes a little bit of energy. So if you think back to Gen Chem, you have to add a little bit of energy for it to be at almost like a half bond. It's attracted right now to that hydrogen, but then it goes boom and it snaps this off. So we have actually a decrease in energy to where we get that alkyl oxonium ion. Okay. Then if you look at the next step, it takes a lot of energy to get over the biggest hump. Remember, the biggest hill technically is why it's called the transition. It's why it's the rate limiting step. But on your own, you can look through the others and the rest of this PowerPoint to go over and just understand what that means. And in the next class, we're going to talk about Sn2 reaction. There's Sn1 reaction mechanism, but then we'll talk about an Sn2 reaction mechanism.